Okay. Okay. So I think this is lecture number 9. Okay. So sorry, it's lecture number 9. Welcome to lecture number 9. So yesterday we saw the second proof of analysis of a randomized quicksort. Today we are going to focus mainly on the average case analysis of quicksort, and possibly we'll define the problem of median finding and give a randomized solution, or else we'll do in the next lecture. Okay. So let me begin with the description of worst case analysis of quicksort, and then we'll arrive at the definition of average case analysis. I'm sure many of you must have heard that average case complexity of quicksort algorithm is order of n log n, right? I don't know if you have done a rigorous proof of it, but I'm sure most of you have heard about it, right? So we are going to formalize what is average case analysis, particularly for sorting algorithms, and we are going to kind of see that average case analysis is pretty much equivalent to the analysis of randomized quicksort. That's it. Okay, so that's what we're going to do today. We'll set up the conditions for which this equivalence can be done, and then we leave it. We will not do average case analysis. We just see that analysis of randomized quicksort already gives us what we require. Okay. Just try to understand the worst case complexity. Okay. So I've already described the way we define worst case complexity. So let's say abstractly, A is some algorithm, okay, for some given problem. Could be any of your favorite problems. The worst case complexity of A is defined to be, so let's say W of n. So where n measures the input length, max taken over all inputs of length n. So A of I. So A of I is just abuse of notation saying that A of I represents the performance of A on input I. Okay. Now performance could be anything. In our case, in the case of quicksort, we were looking at comparisons. In the case of integer multiplication, we were looking at bit operations. In the case of Strasson's multiplication, it was operation number of arithmetic operations, addition and multiplication. Okay. So now let's just quickly look at what is it in the case of sorting algorithms. So suppose A is a sorting algorithm, sorting an array. Now what is this domain? So when I say max over length of I is equal to n. So if it is a comparison based algorithm, we say that domain is not restricted, right? Yeah. So set of all inputs length n is equal to set of all arrays of length n. Okay. But what is that number? Which is an infinite set. Okay. So with this notation, the difficulty is the max runs through an infinite set. Okay. So how would we generally overcome? See, infinite set is not really a big issue. So what you do is we just take an arbitrary array and do the analysis. And assume the worst possible scenarios, usually we end up with the worst possible input or worst case upper bound. So as such, infinite set is not really a problem here, but we need to remember that this is, so when I say max here, it's over an infinite set, not a finite set. Okay. But for most of our analysis, I mean, so far we have seen only analysis of quicksort. It really did not matter because we started with an arbitrary array of length n and did the analysis. Okay. So that way it's not a big deal as such. But it creates trouble when we try to define average case analysis or average case complexity. Okay, so let's try to define average case complexity. So intuitively, average case essentially means we replace this max by average. Okay. The average case complexity of the algorithm A would be Tn is the average taken over all inputs of length n, the performance of A on that particular input. Equivalently, what is average? Tn should be 1 by size of I summation actual input and performance of the algorithm on that input. Okay. But in the case of arrays, we saw that I, so in the case of sorting or in the case of comparison based sorting, this set I, script I is infinite. Right? So 1 by size of I does not make sense. It's 0, right? Then everything will become 0. So yeah, the question is, how do we overcome this? I mean, I'm sure all of you have heard of the fact that quicksort has average case complexity of n log n. Can anybody confirm?
Yes, sir.
Yes, right? So that means there should be a way out of it, right? This should not be the definition. So I hope everybody appreciate the problem with the definition here, right? See, average case is,
Sir, I have a question.
yes, yes.
So here ASI denotes the output or the time taken for that input I.
So the measure, okay. Any measure, so time taken or comparison, whatever you are interested in.
Okay, thanks.
Yeah. Sorry, this should be script I. Okay, so this is not. This should have been script I. Yeah, so I'm just abusing the notation. Okay, so I'm using the same symbol as algorithm and say A of input to say whatever measure that we are interested in. Could be comparison, space complexity, time complexity, whatever we are interested in. Okay. Yeah. So for the next few minutes, we are going to see a way out of it and we'll give a justification to it. Yeah. So most of the lecture is essentially that. Okay. So we'll see a way out of it and then give a justification and then see that this way out of it immediately tells us that average case complexity of quicksort is essentially the expected running time of our randomized quicksort. That's it. Okay. So that's what we are going to do the rest of the lecture. Okay, so this is exactly what I said. So since there is no restriction on the elements, there are infinitely many inputs of length n. So, or in other words, I is infinite. So, yeah. So how do we do average case analysis? So before I move to the next slide, I just wait for a minute to hear from you. What will be the way out? Or what do you think could be the way out? Any thoughts?
Maybe take the input as an average case, like an average input like that contains not the worst case, not the best case, but the
Yeah, but how do
numbers
you
are
do that?
arranged.
Yes, how do you do that? When you say average case, right? How is it defined? When you say, I mean, ideally, when you say average case, pick an input uniformly at random from the set of all inputs, right?
Yes.
But what you have is an infinite discrete set, right? Do you have an uniform measure on it?
At
Maybe we
one
can
level,
take
we can use
any.
worst case, and at the level below it, we can use the best case, and then the um, combination of both means at one level worst, at that next level best, then worst, then best.
But how do you justify? Why is it the average case?
Sir, because at every point we are considering both best and both worst case, therefore on average it will be the average case.
No, but again, see, what do you average on, right? If you take best case, worst case, but there are infinite elements, right? See, the problem is averaging over an infinite set, right? Number of elements is infinite. That is what we have trouble in, right?
If we can fix the elements to be distinct and we can take any n elements and try to formulate our average on that, then our set won't be infinite.
Okay, that's a very good solution. So once you fix n distinct elements and then take average on rearrangements of it, right? That's what you mean.
Yeah,
Yeah,
yeah, yeah.
that's a very good solution. In fact, that is a solution that we are going to do. All we are going to do is we will justify why it can be done. Okay. So yeah, any other thoughts? I think your voice is very low. Can you speak closer to the mic? Yeah,
Now is
Milan.
it, now is it fine?
Yes, it is fine. Yeah, go
So
ahead.
like we can have n possibilities for the pivot 9 case of quicksort.
Yes.
So corresponding to different n possibilities, we can have different n time complexities.
Yeah, but see, average should be average over the inputs, right? So how do you do that? So what you're saying is, I mean, we'll just choose all. I mean, we will consider all possibilities of the pivot, but overall, I mean, it should be. See, when you take average, it should be like it should be a domain where you have uniform distribution, right? The weight should be equal to each. So in this process, you have to ensure that all inputs get equal weightage.
Okay.
That is the challenge, right?
Um,
And see, particularly, so when see infinite domain is as such not a problem. So if it was a continuous domain, right, you know how to sample. So say if it is set of all real numbers, there is a way to sample real numbers in a particular interval. It can be done. But whereas in a discrete domain, if you have a discrete set which is infinite, yeah, so defining uniform measure, I don't think it is known how to do it. Okay, so there's no easy way unless you approximate it with some continuous domain and then do that. But then what happens is if you approximate it with the continuous domain, suddenly then your measure drops to zero. Okay, so that is a difficulty. But the solution is, I don't remember I mean, I didn't see the name. One of you had suggested. You just fix n distinct elements and permute them. And we'll see that surprisingly it just works. Okay, we'll give formal justification of it. Okay, so before that I'll just give you a definition. Okay, so let's say you have an array A. Let pi A denote the set of all permutations of the array. Okay, so let me give a concrete example. Let's say the array is 437. I'm just using the tuple notation to represent arrays. Okay, so arrays of 3 elements. So how many permutations of 3 elements? 3 factorial, which is 6, right? So pi of 437 is exactly this set. So 437, 473, 347, 37, 4, 34, 743, and 734. Okay, exactly 6 elements. Yeah, is the definition clear? So this is exactly one of your classmates was talking about. You rearrange a given array. So the rearrangement is formally denoted as pi of that array. Yeah, and there are exactly, if arrays of length n, exactly n factorial such. Okay. So now I'm going to define the average case complexity as the following. Okay. So for now I'm zeroing, I'm not considering an arbitrary algorithm for an arbitrary problem. Instead, we are talking about sorting algorithm. Okay. So suppose A is a comparison based sorting algorithm. Okay. That is crucial. It should be comparison based. The average complexity or average case complexity of A, we define it as P of n is equal to, there is a max of course. So max over all arrays, okay, this value. So this is a weighted average. So 1 by n factorial times sum of the complexities of the algorithm on permutations of this array. So I run over all permutations of this array, which we denote by pi of a. Okay, I take average. Yeah, where the max is taken over all arrays of length n. Yeah, I cheated, right? I said average case and I'm suddenly putting in max. Isn't it cheating? I mean, how can you put max for average case? Average case should be average, right? Where is average here? Okay, average is here, but I'm taking maximum here. Isn't that kind of cheating? Yeah.
So we are removing the worst case of the given set of array.
Yeah. So yeah, but put it more precisely. This is worst of the averages, right?
Yes.
This is worst of the averages.
Yes.
But in absolute terms, this is incorrect. Okay. In absolute terms, this is incorrect. Should not be absolute average case. I want average of over all inputs, right? If somebody says, when I say average, average should be average over all inputs. But what I'm doing is I'm grouping the inputs and taking average within the groups and then taking the worst case. So then there is also worst case, right? When I say max, it's already worst case. Okay. But the interesting part is for comparison based algorithm, if we put some kind of restrictions on the comparison, this max is irrelevant. Okay. Yeah. Again, one difficulty is max is again over an infinite domain. But the point is the max is going to be irrelevant. In other words, this value is not going to be different if you vary A. This value is going to be the same for all arrays. Yeah,
Hello.
yeah, yes, yes.
I don't understand. Okay, you have an infinite set of arrays of length n. That is A.
That's a variable. I mean, so A runs over all those arrays.
A is not the set. Okay.
A is not the set. A runs
Okay.
over. So max A, right? A is, I mean, the choice for A is described here, where the max is taken over all arrays A of length n, which is an infinite set. A
Okay.
itself is not infinite. A is
So
array of
we
length
haven't become any better now. Have we become any better now?
slightly better, right? We don't have 1 by infinity anywhere, right?
But still, the set is infinite.
But we are taking maximum over that, right? We don't have the trouble of defining uniform distribution over that set, infinite set.
Sure.
But what I mean is, I mean, this should not be the average case, right? I mean, I should give justification for that. Okay, this is actually the average case,
Yes, yes. Because you're
right?
taking the max of the entire set again. You're taking the
Exactly.
average of individual arrays permutations and then taking the max over that. So it's
Yeah.
somewhere not feeling it's somewhere intuitively feeling that it's not an average.
Exactly. Okay. So the rest of the lecture, we are going to give full justification for this. The justification is fairly simple. Uh, okay. So one kind of simplification I'm going to assume, otherwise our arguments will not work. is that, see, I think a couple of lectures ago, I just said, okay, sorting algorithm. So comparisons, when we say, so if you compare A less than 100, we just charge it as one comparison. Okay, or any of the loop invariants, we charge it as a comparison. Okay, for now I'm going to go back on that statement. What I'm going to say is, like, for now, let's assume when we say comparison between two elements of the array. Any other comparison we are going to ignore. We are not going to count it. Okay. So comparisons, we count only those that are between two elements of the array. Okay. So this is actually simplifying assumption. I don't have complete justification. I think it can be justified, but this is just a simplifying assumption. Okay. Other comparisons we don't account for, and we'll also assume that other than loop invariants, the algorithm does not make any other comparison. Okay. You might argue, okay, maybe I can come up with a better algorithm. It is possible, but as far as I understand, it should not be possible. But I'm not going to give rigorous reasoning. Say, for example, if somebody writes an algorithm which compares, say, A less than 100, okay, our argument is not going to work for such an algorithm. Okay, but in that case, I'll just brush it aside, saying that, okay, if you're saying A less than 100, you're making knowledge. So you're gaining knowledge about the actual values. So when I say comparison based algorithms, the assumption is you don't have any knowledge about the actual values. Only thing that you are going to do is compare two elements. Okay, is everything fine? There was some alert. Okay, so there were some, okay. Okay, so there were messages. Okay, thank you. So, okay, so when you say A less than 100, you're gaining knowledge about the element, right? So usually the assumption for comparison based algorithms is you don't try to get any knowledge about the actual values. So in that sense, it is justified. Let's not spend too much time on justifying it. So let's just make this as an assumption. Okay. So assumption is the comparison is between any two elements of the array. Okay. So under this assumption, we have the following statement. Okay. So this is our main theorem. So consider any comparison based sorting algorithm. Let's call it as script A. Let B be any array with n distinct elements. So that is again, I mean, so I've always been assuming that array has n distinct elements. So many of you would be having in mind, okay, what happens if I have repeated elements and so on? See, there are multiple ways of overcoming it. Okay, so if you have repeated elements, one thing is you remove the duplicate. But of course, algorithmically, it's not easy. Removing the duplicate also will require significant amount of time. But for analysis sake, you can just remove the duplicates. Another way to see is if you have repeated elements, say element 100 is repeating twice. What I'll do is, okay, we'll change the domain to rational numbers and add slight epsilon. Okay, so that these elements are distinct. And finally, after the sorting completes, you just restore it to back to original values. Okay, so that is another way of seeing it. But usually repeated elements don't do harm. Okay, if at all, our algorithm will be bad on distinct elements. So that's why we make this assumption. Don't break your head too much on it. So let's just keep this as the assumption. Okay, yeah, so B be any array with n distinct elements. Then the claim is there is an array B prime consisting of distinct values from 1 to n. In fact, there is a unique array. Okay, so there is a unique array such that the complexity of A on B is the same as complexity of A on B prime. Okay, so let's draw it pictorially. So if you have B, an array, okay, I can come up with an array B prime with the values from 1 to n, okay, such that a of b is the same as a of b prime. There is also kind of bijective correspondence, but I'm not going to specify it. That is, when I say bijective, so if I consider permutations of b, it will correspond to permutations of b prime. Okay, so that way there is a bijective correspondence, and in a sense, this array is unique among all arrays with values from 1 to n, distinct values from n to n, which is nothing but permutations of 1 to n. Okay. Any question on the statement?
Sir,
Sir,
the
how
ordering of
big
B
and
prime.
Okay, two people are speaking, or there was some echo kind of thing. Can you repeat the question?
Yeah, I was just asking that the ordering of B prime will be according to the array B, so that A of B is equal to A of B prime.
Yeah, so see, this ordering, I was not really specific about it. So what I meant was, if you consider any permutations of B, right, then the corresponding array will be actually the corresponding permutation of B prime. That's what it means. Okay.
Okay. Yeah.
Yeah, we'll see it in the construction. Okay, I didn't write that in the formal statement because it will make the statement, already it's lengthy and it will make it more messy. When we construct the array, it will be clear. Yeah. So there was one more person wanting to say something.
So that was only how B is different to B prime.
Yeah, so B could be anything. Okay, B could be, say, elements. I mean, the least element is n square and the largest element is 2 power n, whatever. It's unbounded. Okay, there is no restriction on the values. Whereas B prime takes values only from 1 to n, nothing more.
Okay, sir.
Yeah. Okay. So yeah, so we'll construction is just one line. Okay. So all we do is, so we construct B prime from B by replacing the ith smallest element, or in formal terms, element of rank I element in B by just the value I. That's it. Replacing the element by its rank. Let me be concrete with the example. Okay. So let's take this array of 5 elements. Okay. So what are the ranks? Let me write down the ranks quickly. Smallest element is 6, so rank 1. Oh, sorry. This is rank 1. This is rank 2. This is rank 3. This is rank 4. This is rank 5. Okay. Yeah. So now my array is just this upper part. So B prime is 5 here, then 3 here, then 2 here, then 4 here, then 6. Instead of 6, it will be 1. Okay. That is all. Is the construction of B prime clear? We just replace the elements by their ranks. Now the claim is any sorting algorithm which is comparison based. So again, we need that restriction that when I say comparison between two elements of the array, okay, not arbitrary comparison. The algorithm, output of the algorithm, what do I mean by output of the algorithm? The permutation is going to be the same. Not only that the output of the algorithm is same, the complexity is going to be the same. That is more crucial to us. The complexity of A on B is the same as complexity of A on B prime. So I'll just prove it quickly. Okay. So proof is just one line, okay, not even formal argument, just one picture. That's it. So let's look at, yeah, any question on the construction quickly?
Sir, I have a question in the previous slide.
Okay. This one, sorry, this one?
Yes, sir. Sir,
Yeah.
here if n is fixed, that is, we are taking n distinct elements.
Yes.
Then how can, I mean, why max is an infinite domain?
So remember, so max is taken over all arrays, right, of length n. So how many arrays of length n if you don't fix any bound on the values, right?
Sir, but we are taking n distinct, means we have fixed n distinct elements.
No. So taken over all arrays of length n. So all arrays with distinct elements. These distinct elements could be anything, right? Any natural number.
Okay.
So there are infinitely many arrays of length n, right? That is what this does. But only thing is the elements are distinct. You don't have duplication. That is for simplicity. Okay. For our analysis, it just works easier if you have distinct elements.
Yes, sir.
Okay. Yeah.
Sir,
Huh?
one question. Sir, why you said because this is an infinite domain because the values are different, right? But why we are interested in the values? We are only interested in like the permutations, right? Like for an array, there will be like even if the elements are distinct,
Yeah.
for an array of length n, there is like fixed rank, right? For each of that
That's exactly
whatever.
what we are going to do. I mean, that's what we are doing now. We are just
Okay.
saying the values are irrelevant. It's only the, I mean, it's enough to consider permutations of 120. That's exactly what we are seeing now.
Okay. Okay, sir.
Yeah. 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 Any other question? Okay. So now we just need one line justification of this construction. Okay. Uh, so this is exactly what the person who asked last. Can I know your name? Okay.
Sir, me?
So yeah. So I can't see the names. Yeah.
Yeah,
So yeah. So we are
Shira.
proving exactly the, yeah, Shira. Okay. So we are proving exactly the statement that Shira made. Okay. But that's just one line proof. Okay. Yeah. So now let's consider the two scenarios. So this is A. Oh, sorry. A on B. This is A on B prime. Okay. So this A is script A. Okay. My handwriting is bad. So let's look at one comparison to begin with. Okay, the first comparison they make is the same, right? So I said we are not counting any other comparison as comparison. So comparison between two elements of the array is what we are going to look at. Yeah. So until the first comparison, the algorithm does not have any other information, right? So it will be, let's say it's comparing element of rank I with element of rank J. Okay. So what does the corresponding comparison here? I versus J. Okay. Because element of rank I is I, element of rank J is J. Now the outcome is I less than J, AI less than AJ, or AI greater than or equal to AJ. So the corresponding outcome is I less than J, I greater than or equal to J. Now by the construction, AI is less than AJ if and only if I less than J. That is, element of rank I is less than element of rank J if and only if I is less than J. Remember that elements are distinct, right? So you take a left branch on B if and only if you are going to take a left branch on B prime. You take a right branch on B if and only if you are going to take a right branch. So once the first path is fixed, of the subsequent comparisons, it's the same result, right? So the outcome is going to be the same. Sorry. It really does not matter. Or in other words, the algorithm won't be able to differentiate between B and B prime. Any comparison based algorithm, it will be oblivious to these two arrays. The behavior will be the same. When I say behavior, the end node that you reach, right? The final output you are going to make, it's going to be the same. So what was the final output? If you look at our lower bound argument, right, our intuition, I mean, our interpretation was you will consider only the permutation. So the final permutation that it requires to apply on the array so that the array becomes sorted is going to be the same. Not only that, the comparisons made are exactly the same. When I say exactly the same, the the position of the elements being compared, they are going to be the same. They won't be different. Okay. Or in other words, like Shira said, right? It's enough to consider one specific array. So in this case, we are just considering elements to be from 1 to n and consider its permutation. The behavior is going to be exactly same for any other array. That is, come with any array B, I can come up with the unique array B prime with elements from 1 to n such that the behavior of the algorithm is the same on B and B prime. Now from this construction, what I have written in the statement here is one more thing. If you consider any permutation of it, the behavior is the same if you apply the corresponding permutation of B on B prime. So they are equivalent in that sense. So if you permute B, you can apply the corresponding permutation on B prime. That is going to be your array on 1 to n, which has the same complexity as the permutation of B. Okay. So that way there is a bijective correspondence, what I haven't said in the statement here. Okay. So in other words, let's just go back and stare at this expression here. Yeah. So this max is not even relevant. If you consider A as array just 1 to n and consider all permutation, this quantity is invariant if you replace A with any other array of your choice. That is any of the infinitely many arrays. So the max is kind of obsolete. The value does not differ. That's because the fundamental reason being the algorithm is comparison based. You don't really rely on the values. You only rely on their relations, how the values are related to each other. See, comparison is basically comparing two elements is basically seeing the relationship between them with respect to the less than or equal to relation, right? The partial order. So what matters is how they are relatively positioned with respect to the less than or equal to relation. It really does not matter what values they are. Which is kind of justified because when we say comparison based algorithm, the algorithm does not depend on the values at all, right? It's not supposed to look into the values. It's only supposed to compare the values. So if comparison is the only allowed operation, that is comparison between two elements, then all that matters is how they are mutually related to each other, not what values they are. Okay, so that's the reason why many of you would have also seen in textbooks. Yes.
Yeah, I have just a question. So why in first place have we written a
Yes.
max in the definition?
So I said max because I don't know how to do average, right? So I'll take the worst case possibility there.
So you just trying
See, I
to
could
make
have
a
written
proxy there.
yeah. Yeah, see, otherwise, how do I consider, right? I mean, in the sense that from an infinite domain, I cannot average. So I came up with a finite domain where I can average. Then maybe I'll just consider the worst case there, just to be safe. I mean, you could have considered minimum, but then it won't be, people will not accept it as average case as such, right? Then what happens to values other than that? Ideally, it should have been average, but average we cannot do. So that's why I proposed max.
Okay.
Okay.
Thanks.
But the point is, I mean, it was irrelevant as such. For the sorting algorithm, it was completely irrelevant. This max or min, it really does not matter because all these values are going to be the same. That is an important point. I mean, I don't have a complete justification of why should it be max. It's just a proposal. It was just a proposal.
Yeah, anyhow, only the partial ordering matters, so it doesn't make a difference.
Exactly. That's all. Okay. So this is the formal statement. So then the comparison outcomes of the comparisons are the same for B and B prime. That is, a comparison based algorithm will not be able to distinguish between these two arrays. Okay, it's only relative order. So this is why you might have seen in your textbooks or previous algorithms courses, people usually analyze sorting algorithm when the array consists of elements from 1 to n. You might have noticed it, right? And this is the reason, because any comparison based algorithm, it only looks at the relative ordering of the elements. It really does not look at the values. Okay, so yeah, yeah. So this is the statement. A will do the same number of comparisons on B and as well as on B prime. It won't be able to distinguish. Okay. Yeah. So what is the use of this theorem? I mean, theorem uses, we have a simple definition for average case complexity now, right? So the average case complexity of any comparison based sorting algorithm, it need not be sorting, any comparison based algorithm. I mean, any algorithm where we only bother about the number of comparisons made is given by 1 by n factorial times the sum of the complexities, that is number of comparisons made by the algorithm on all permutations of 1 to n. Okay, so where this notation is pi of this is set of all n element arrays obtained by permuting 1 to n. I'm just for convenience, I've just given examples. Okay, so pi of 3 is basically this 6 element set. Pi of 4 is this 24 element set. All permutations of 1, 2, 3, 4. Okay. So yeah, so now the definition is fairly simple, right? I mean, this is what you would have seen in many textbooks or in your previous courses. Okay. And I hope this justification clears it out why this can be done formally. Yeah. Okay, so this is just a formal statement of what we have concluded. Okay. Yeah, so before moving further, I think 45, so we have time. So just 1 minute for any question.
Hello, sir.
Yes.
So basically, I understood the whole proof and all the thing, and also the means just one doubt I was having was when you were comparing comparison on B prime. I just didn't understood the way you were comparing. Otherwise, I understood that the number of comparison will be same irrespective of the fact what is the elements in the array. Yes,
Okay.
this tree based method I didn't understood.
See, I mean, so tree is basically mapping the comparisons, right? The first node in the tree corresponds to the first comparison of the algorithm. Okay. So if you take left branch, that means the outcome is so AI less than AJ, then this node represents the second comparison. So similarly, if the outcome was AI greater or equal to AJ, this node represents the second comparison, and so on. So this is basically mapping all possible comparisons made by the algorithm and the corresponding outcomes. So one particular instance basically will be tracing a path.
Yeah.
So if the actual outcome was this, then you will take this path and so on. This is basically a decision tree. Okay.
Okay.
You have
So basically, both the tree will be same. Yeah.
Exactly. So this is how we proved lower bound, if you remember, some 3 lectures ago, 3, 4 lectures ago. Okay. So we consider this decision tree. Yeah. Yeah. Is that clear? Okay. Now I'll move on. Okay. Yeah. Now the question is, okay, you did, so I did this randomized quicksort, then I suddenly jumped into average case. What is the connection, right? I mean, I would not do it if there is no connection as such. Okay, so now in the next few minutes, I'm going to establish that our analysis of randomized quicksort essentially gives us average case complexity of quicksort. Okay, so that is what I'm going to justify. So for that, we'll take a probabilistic view of this average case analysis, which is, I mean, nothing out of the blue. I mean, it's the same thing restated in a different way. Okay.
Sir, just a clarification.
Yes.
So when we are analyzing the average case, we have fixed the pivot at every stage. It was not a randomly checking, selecting the pivot.
I'm coming to that's a very good question. Okay, so when we do average case analysis, we'll need a deterministic quicksort. Okay, I'll fix that version. when we do the analysis. Okay, in the next
Sure.
slide, we are going to fix the version of quicksort we are going to analyze.
Thank
Okay?
you. Thank you. Okay, sir. Okay.
Yeah. Okay. So this was our definition of average case complexity of any algorithm. Okay. So this is nothing but if you sample an array uniformly at random from this set, that is set of all permutations of 1 to n, and you look at the expectation. This is exactly that, right? Yeah. So this expression is nothing but expectation of the performance of A, or that is number of comparisons of A, when we choose an array uniformly at random from set of all permutations of 1 to n. That are exactly n factorial many. So probability of hitting upon a particular array is 1 by n factorial. So this is it. Okay. So you can take a probabilistic view. So you can imagine you're running your favorite version of quicksort on a random array. That is a random permutation of 1 to n. Okay. So that is the imagination that we are going to take. So like one of you had asked, so we are going to fix the quicksort. Okay. So this is our choice. I mean, it really does not matter. So I'll just take the simplest version first. Okay. So the version of quicksort that we are going to analyze is we choose the first element as the pivot always. Okay. Now you can ask, oh, why not the last element or why not the middle element? Analysis is going to be the same. Okay. So let's make it simple. So I just consider the first element, then partition the array into left, middle, and right based on the first element, and then recursively sort L and R, output LMR. That's our quicksort. Okay. So instead of random pivot, we are going to choose the first element. Now, many of you might question, okay, so why can't I do average case analysis on randomized quicksort and so on? Yes, you can do. Let's simplify things first. Okay, so let's consider the deterministic version. Let's not complicate. See, I already stated that we are going to take a probabilistic view where the array is sampled uniformly at random from the set of all permutations. And then if you again choose randomly a pivot, it's going to complicate matters, right? There are already two randomness. So when you compute expectation and all, it's going to be confusing. So let's not do average case analysis of randomized quicksort. Instead, let's consider a simplest version where the first element is pivot. Okay. So our algorithm A is this quicksort algorithm, and this is the quantity we want to estimate, the expected value of number of comparisons made by quicksort when, remember, we are choosing array at random, or in other words, equivalently, we are choosing a pi permutation of 1 to n, chosen it uniformly at random. Chosen uniformly at random. Okay, so it's already 8:50. I'll take 3 minutes more. Okay, Srinivasa, just remind me when it is say 8:55. Okay. Okay. So.
Yes, sir. I'll do that, sir.
Yes. So yeah. So now let's establish the connection. Okay. So suppose A is chosen uniformly at random. That is, A is a permutation of 1 to n. Okay. Now what is the first element? Let's try to understand that. So if I choose A is a random permutation, of 1 to n. Yeah. So fix any I, okay, I from 1 to n. What is the probability that first element is I?
One by n.
1 by n. Why is that?
So because it could be any of n elements, any I
yeah,
from.
Yeah, but why is that? So we need a justification, right?
Because all the elements are distinct here.
Yeah, but so we should show the computation probability, right?
So because
There are
all the
total of
elements.
n.
They are
Sorry.
Because there are
uniformly distributed.
because there are a
Okay.
total of n factorial ways we can arrange, and out of them in n minus 1 factorial ways, that element will come at the first place.
Very good. That's the right answer. Okay, so the last one is the right answer. Okay, so what is this probability? This probability is the number of arrays A such that A of 1 is I. Sorry. This is not correct. Not number of arrays. Yeah, number of arrays. It's equivalent, but yeah. So number of permutations. Okay, let's use the permutation language. It's easy. Number of permutations pi such that first position in pi is I divided by total number of permutations. Okay, I'm sorry. Yeah, divided by total number of permutations. See, we are choosing a permutation uniformly at random, right? We have n factorial permutations. So hitting upon any permutation is exactly 1 by the number of permutations, which is n factorial of permutations. So our favorable event is choosing a permutation where the first position is I. So it should be I here. Okay. So if you fix the first position as I, how many permutations of the remaining elements? Exactly n minus 1 factorial. Right? So this is equal to n minus 1 factorial divided by n factorial, which is n by 1 by n. Sorry. This is the formal justification. Okay. So the probability that the first element is I is the number of permutations where the first element is I divided by total number of permutations, because we are randomly sampling a permutation, which is exactly 1 by n. Which, yeah, yes.
So it's 855, sir.
Okay. Yeah, I'll stop. Okay. So in other words, the first element is uniformly at random, right? So this is true for any I. So it's equivalent to choosing an element at random. Or in other words, when you feed the quicksort an array which is chosen uniformly at random among the permutations of 1 to n, it's pretty much like running a randomized quicksort. Okay. Now the question is, will the same thing hold for subsequent iterations? Yes, it does. Okay, next lecture I'm not going to prove it, because proving it rigorously will require a bit more deeper knowledge of permutations and random permutations. We'll not do that, but I'll just write a statement. Even for subsequent iterations or subsequent recursive calls, the same thing is going to do. I mean, in the sense that you don't have to permit it once again, the same permutation, it will work. Okay. So in other words, running quicksort on a random permutation of 1 to n is the same as, I mean, when I say quicksort, our version of quicksort, deterministic quicksort, it's the same as running our randomized quicksort. That's it. So the expected running time becomes expected running time of our quicksort, and that is the connection. Okay, so that's the reason why we talked about average case analysis of quicksort along with randomized quicksort. Yeah, I'll have a couple of more statements to make in the next lecture, but like I said, I'm not going to give complete rigorous proof of this fact. Only this fact is rigorous, but the subsequent iterations, like I said, it requires a bit more knowledge about random permutations, which we will not do. But yeah, so trust me, it works. Okay. Okay, so we'll stop now. We'll meet for a tutorial on Friday, and we're going to release assignment, I think 26th. Okay, so yeah. Okay.